guys, I'm back to follow up my last video where we learned something pretty powerful. We learned that there's this really powerful connection between exponents and radicals. And we knew that. We knew that they were inverse operations. We knew that they cancel each other out. We knew that they were very, very related, right? But in our last lesson, we learned that we can actually jump back and forth between radical form and exponential form. And we can use both of these forms, and they're related in this really powerful way, right? With division. So we learned that if we have a radical, we can rewrite it in exponential form using the operation of division. Because when we are taking a root, all we're doing is we're taking whatever is under the radical, and we're taking out groups according to whatever that root is, whatever the index of that root is. We're taking out groups of that many. So if our index is 3, we're taking out groups of 3. And so we're subtracting groups of 3 off of our radicand. And what is repeated subtraction, you guys? It's division, right? That's what we learned. So we learned that there's this powerful connection between exponential form and radical form, and they are somehow related using division. So I'm going to sort of write in math form a general rule for this, what we learned in our last video. So we learned that when we have a radical, okay, with the kth index, and you know what I'm going to do? I'm going to put that in red. Okay, so when we have a radical with index k, I should say, okay, and it's being raised to the nth power, the radicand is being raised to the nth power. Well, we now know we can rewrite this in exponential form, where we take our base, our radicand, right, to the nth power, and divide it by whatever our index is. And we saw this with our example from the last video. In the last video, we worked with the 5th root of x to the 20th. And we learned that when we had this example, we had 20 copies of x underneath our radical, and we needed to pull out groups of 5. And that's what we did. We kept pulling out group of 5 after group of 5. So we kept subtracting those 5s out of this 20. And when we did so, we saw that it simplified to x to the 20th divided by 5, right? That's what we actually were doing. We were taking those 20 copies, pulling out in groups of 5, and it was 20 divided by 5, which left us with x to the 4th. That simplified to x to the 4th. So we saw that all we were doing was taking this group of 20 x's and pulling out groups of 5. We were taking 20 and dividing them into groups of 5, which left us with x to the 4th on the outside, okay? So this simplified to x to the 4th. So this and this are actually completely equivalent, okay? It's that powerful connection between radicals and exponents, and we can use it to make our life really a whole lot easier, you guys. So I'm going to leave this general rule here, and we're going to be referring back to it throughout this video. So I'm just going to leave it right up top here so we can refer back to it. And so we've learned that we can jump back and forth between radical and exponential form. And when we do, I should actually put this up here. Okay, when we rewrite our radical with an exponent instead, well, in our numerator is always going to go the original exponent that we were raising our radicand to, right? So with our example, it was x to the 20th, our 20 went on top. And then what goes on the bottom, the denominator of that fraction, is going to be the index, right? So whatever your index is goes on the bottom. And for us, it was, we had x to the 20th, we were taking the 5th root. So it was x to the 20th divided by 5, because 5 was our index, okay? So we can go back and forth between these two forms really easily. And it works in both directions. So let's quickly look at an example where we start with an exponent and we rewrite it in radical form. I just want you guys to see it works in both directions. So let's say we had 9 to the 3/2 power, how could we rewrite that as a radical? Okay, so now I want to go from exponential form to radical form. Well, I know that on top is my exponent. Okay, that's how many copies I'm starting with. So if I write my radical here, I'm starting with 3 copies of 9, and I'm pulling out groups of 2. So 2 must be my index. All right, I'm looking for groups of 2 copies. So this expression and this expression are exactly the same, okay? All right, so I'm going to get rid of this. I just wanted to show you that it does indeed work both ways. And now I'm going to show you how this is going to make our life really easy when we are simplifying radical expressions that are a lot more complicated. So let's look at this example. So we've done examples where we've had just numbers as our radicand. We've done examples where we've had variables as our radicand, but we haven't really put all of that together yet. So let's take a look at that. So I'm going to use the cube root of 24 x to the 9th. You know what I'm going to do? I'm going to use different colors. You guys know I love colors. X to the 9th, y to the 15th. Now this is the most complicated radical expression I have given you to simplify. So I want to simplify this. Well, you guys know I always say that multiplication is the best operation, hands down, in algebra, right? Because it allows us to pull things apart really easily. So what I'm going to do is I'm going to take this very long, complicated radical expression here, and I'm going to break it into pieces. I'm going to break it into a number piece, into my variable x, a piece with just my variable x, and a piece with just my variable y. And you're going to see why I do that in a minute. So let me do that. So here I'm going to take my number, break it into the first piece. Okay, there's my first piece. And now I'm going to take my variable x piece here. And now I'm going to take my variable y piece here. So all I'm saying is that the cube root of 24 x to the 9th y to the 15th is equal to the cube root of 24 times the cube root of x to the 9th times the cube root of y to the 15th. Okay, I just literally just broke it into those pieces. So now I have 1, 2, 3 pieces. And the beauty of this is now I can deal with them one piece at a time rather than trying to think about this whole thing at once. So I'm just going to start with my number piece, okay? The cube root of 24. And we know how to deal with this, you guys, okay? We know that when we're taking the cube root of a number, we break it into its prime factorization. So I am looking for, I'm going to break it into its prime factorization and pull out anything that I have 3 copies of, right? My index tells me how many copies to look for. So 24, that's 8 times 3, and any 2 factors will work. 3 is prime, but 8 is not, so I need to keep going. That's 2 times 4. Okay, 2 is prime, but 4 is not, but 4 is equal to 2. Let me scroll down a little. Times 2. So now I have my prime factorization, right? I know that the cube root of 24 is equivalent to the cube root of 2 times 2 times 2 times 3. So let me write that. 2 times 2 times 2 times 3. Okay. And do I have a group of 3 there, you guys? Spin in my little index right there. I do. I have a group of 3 2s, as a matter of fact. Okay. So my index told me I was looking for anything where I had 3 copies. I have 3 copies of 2 right here. So those are going to pull out. So remember, 3 2s on the inside translates to 1 2 on the outside. Okay. And then I'm left with this lonely 3 here. So my cube root of 24 simplifies to 2 cube roots of 3. All right. So I've now simplified. I'm going to make this just bigger so it doesn't blend in with the index. I've now simplified my first piece, okay? And remember, I had 3 pieces, so I'm not done. I'm going to circle this first piece so I don't lose track of it, because that's going to be an important part of our final answer. So now I can move on to my second piece, okay? So this was my first piece. I simplified my first piece. Now let me move on to my second piece, which is, of course, this cube root of x to the 9th. Well, you guys, what did I just learn? I just learned that I can rewrite this, okay, in exponential form. In fact, all I need to do is take my base to the exponent form and divide it by my index. So if I rewrite this, I take my base x to the 9th, my exponent goes in the numerator, my index goes in the denominator, and this, what's 9 divided by 3, you guys? This simplifies to x cubed, okay? So do you see how much easier that made my life? All I had to do was divide the exponent by the index, and boom, I'm left with my answer, okay? Now I've dealt with my first piece, I've dealt with my second piece, I need to deal with my third piece over here, and I'm just going to do the same thing. So now let me deal with my third piece here, which is the cube root of y to the 15th. I know I can rewrite this in exponential form. So I just take my base, raise it to my exponent power, that's my numerator, divide it by my index, that's my denominator. What's 15 divided by 3? 5. Boom. There's my last piece. So I have my first piece, my number piece, my second piece, my x variable piece, and my third piece, my y variable piece. I need to now put it all together. So I'm going to come over here. So this whole big expression simplifies to, well, my cube root of 24, that simplified to 2 cube roots of 3. Okay. My x to the 9th, that simplified, you know what, actually, hold on, let me rewrite this so I have some more space on the left. So I had 2 cube roots of 3. You always want your radical piece, anything under the radical to the right, and everything else to the left, which is why I wanted to move that over. So now my second piece, my cube root of x to the 9th, well, how did that simplify? That simplified to x cubed. Okay, so we're going to put that out to the left. And then my third piece, my y to the 15th, my cube root of y to the 15th, that simplified to y to the 5th. So I have y to the 5th times x cubed times 2 cube roots of 3. Now, guys, notice how I put my radical all the way over here to the right, okay? I didn't write 2 cube roots of 3 times x to the 5th, x to the 3rd, y to the 5th to the right of it. That's because I don't want to accidentally wind up putting my x to the 3rd, y to the 5th as part of my radical. It would be really, really easy to accidentally do that. So anything that's not underneath your radical, you want to put over here on the left of the radical. Okay? So anything that's not left under the radical, always put to the left of the radical so you don't get it all mixed up. So isn't that nice? We were able to use that powerful rule that we discovered of jumping back and forth between radical and exponential form to simplify this really easily and really nicely, okay? So that's how it simplifies. Isn't that great? All right, so now let's look at an example where it gets just a little bit more complicated. And not really, it's the same concept, but our fractions just aren't going to work out as nicely. And let's talk about what we do in that case, okay? So let's look at the square root of 54x to the 7th, okay? The square root. So remember, when we have a square root, you guys, it's like we have that invisible 2 out there, okay? And again, actually, I'm going to use a color for this, a different color, so we can break it into pieces. So I'm just going to rewrite this in blue. Okay, so again, we're going to break this up into pieces. We don't have as many pieces this time. We're only going to have 2, right? We have our number piece, and we have our variable x piece, okay? So let's rewrite this in pieces. So the square root of 54 times the square root of x to the 7th, okay? Now we have our number piece, we have our first piece here, and we have our variable x piece. So let's deal with the number piece first. We know that when we're taking a root of a number, we break it into its prime factorization. So 54, 9 times 5, or excuse me, 9 times 6. Sorry about that. Get my brush back. Okay, 9 times 6 will give me 54. Neither of those are prime, so I'm going to break 9 into 3 and 3, and 6 into 3 and 2, and as it turns out, all of those are prime. So there's our prime factorization. Okay. All right, so I look at my index. That tells me I'm looking for groups of 2, right? So we know that the square root of 54 is equal to the square root of 3 times 3 times 3 times 2. And do I have a group of 2 anywhere? Remember, my index tells me I'm looking for what I'm looking for. How many copies am I looking for? Copies of 2. So I need a group of 2. I do. I have a group of 2 3s. Okay, I only have one of them. So we're going to pull those out, which is going to give us a 3 on the outside. And what's left on the inside of our radical, you guys? 3 times 2, which is 6. Okay, so this simplifies to 3 radical 6. 3 square roots of 6, I should say. I'm going to circle that because I don't want to lose track of it. This is going to be the first piece of my answer. Now I need to deal with this second piece over here, this x to the 7th, the square root of x to the 7th. So I know from this lovely rule that we discovered that I can rewrite this in exponential form, right? Okay, so I can rewrite this as x to the 7th. My exponent always goes on top. And I'm dividing it into groups of 2. So my index goes on the bottom, right? I'm taking those 7 copies of x and I'm pulling out groups of 2. So 7 copies divided into groups of 2, okay? Well, look at this, you guys. Does 7 divide by 2 easily? It doesn't. Evenly, I should say. It doesn't, right? We're going to have a remainder, okay? And there are 2 different ways that you can think about this. So you can think of it as long division, or you can think of it as a mixed number. And you can decide which way you like better. Let's look at it as long division first. So if we take 7 and we divide it by 2, right? Well, 2 goes into 7 3 times, but I'm going to have this remainder of 1, okay? So that means that I was able to get 3 groups of 2 out, okay? So that represents my exponent on the outside. I got 3 groups out, okay? So that's my outside exponent. But I had 1 left over. So then this 1 is going to represent my inside exponent. So when I did that, I got 3 groups out, okay? So there's my outside exponent. I got 3 groups out. But I was left with 1x still in there, okay? So that's my inside exponent. So this is x cubed times the square root of x, okay? That's one way to think about it. You can think about it using long division, okay? So when you do the long division, however many groups you're able to get out, that's your outside exponent, your 3. And this is how many were left on the inside, okay? One little lowly x was left on the inside. I got 3 copies out, but 1 copy was left in. So I have 3 copies of x out, and I had to leave 1 inside. Okay, it didn't come out. It didn't have 2 other x's to take it outside with it. All right, the other way you can think of this is as a mixed number. Okay, so you can also say to yourself, okay, this 7 over 2 is actually, so let me do it like this. So that exponent 7 over 2 is actually 3 1/2. Okay, you can think of it as a mixed number. And here, this would be your outside exponent. and then this would be your inside. The 1 is your inside. And that 2 that you see on the bottom, you guys, that's just representing our index, right? We know that the denominator is always representing our index, okay? So this 2 just represents our index. So again, we got 3 copies of x out, 1 was left, and this 2 just means that we didn't have another one to pair it with. So that's just representing our index, okay? We were dividing into groups of 2. So our index was, of course, 2. Either way, it gives you the same answer, okay? Your outside exponent is 3. We got 3 copies of x out. We had 1 copy left over, so it had to stay inside the radical, all right? So that's how you deal with a mixed number. You can either do it as long division or a mixed number, or excuse me, that's how you deal with an exponent that doesn't divide evenly. You can either deal with it in long division or as a mixed number, okay? But either way, you're going to get the same answer. So you are now left with x cubed times the square root of x, okay? Now we need to put these 2 pieces together. All right, so let's see how we do that, because we haven't really talked about that yet. So how do we put these 2 pieces together? Well, we have 3 square roots of 6. We have x cubed times the square root of x to the first. Let's start with everything outside of our radical. So we had a 3 outside of our radical and an x cubed outside of our radical. And what did we have inside our radical, you guys? We had a 6 left in there, and then we have an x left in there. So this would be our final answer. Okay, so anything that's outside of the radical goes to the left. Anything that goes inside the radical obviously goes inside of it. All right? So there is our beautiful answer. So as you can see, we can use this rule to really do some more complicated expressions where we now have a combination of numbers and variables as our radicand. And when you do that, you guys, you want to make sure you break it up into pieces, your number piece, and then a piece for each of your variables. And you break it down piece by piece and simplify one piece at a time. And then at the end, you put it all together. All right?